Let's finish off volumes. So far we've looked at a couple of different ways to work out different volumes, right? We've looked at annular slices. Let's just get back in our head. How does it work? When you have a question which you approach by annular slices, right? You do your diagram, you end up with each of your slices looking something like this. Obviously depending on what kind of a volume you've got, okay? And then each of these annular slices, we can work out what their dimensions are. We call that a little radius, which is a function because it can change. We might call this the big radius, which is also a function because it can change. And then, which you can't see at the moment, if I just put a little sort of, there you go. It has a thickness, right, which would be delta y or delta x, depending on which way you are slicing, right? So therefore, when we take this bunch of discs, this bunch of slices, we say the volume will be equal to, and then we form this sum, and we use sigma notation to do that, right? Just for the sake of illustration, let's just consider it delta y, okay? We take a limit. And why do we have to put this in? What is the significance of this limit? What does it mean in this case? It's about making all of these slices very, very, very thin, right? So that we don't have a bunch of slices which are close, like an approximation, but slices of infinitesimally small thinness, so you really actually get the exact volume, not an approximation. All right, so then what do we add up? What do we add up? Or maybe I should say, where do we add up? Because this thing has boundaries, right? Well, I guess it just depends on the volume that they give you. You're going to have, just like an area, an upper bound and a lower bound. Volume. Okay? Right. Now, what is the actual thing that we're adding up? What comes in after here? It belongs here. It's going to be the volume of the slice, is it not? Okay. So we've worked out, we've looked at these annular slices before. There's two circles, so we do the subtraction, you get this. Big circle minus little circle, but that's just an area, right? To make it a volume, we multiply by, in this case, delta y. Okay, cool. So that's the way we approach it, and then of course we recognize that we can work out what this sum is by integration. Okay, and so we write this equivalent integral, yeah? We take that pi out the front, because it's just a constant, from a to b, and then you've got this, and you're integrating with respect to y. Okay, great, no problems. Now, cylindrical shells. It's still a bit fresher in our minds, but I hope you can see the parallel here, right? Instead of getting this kind of shape, right, we divide it up in a different way. This was perpendicular to the axis of rotation. So when we go parallel to the axis of rotation, that's why you get a cylindrical shell. Okay, it's not a cylinder. It's just a shell. That's why I used the piece of paper to illustrate. It's there's no, it's hollow, right? It's completely hollow, which means that if you get a metaphorical or a real pair of, no, that's the wrong way. Sorry, it's the other way. Pair of scissors, right? And you cut the cylindrical shell, you end up with just a rectangle, right? And you saw it, okay? So being that this is a cylinder, it's defined by two dimensions. What are they? What are the dimensions that I can know which will exhaustively define it? I'll need to know the radius, which in turn gives me the circumference, which will be important in a second. And what's the other thing I need to know to work out the cylindrical shell? I need the height, don't I? Okay, so when you cut it open and you unfold it, okay, this 2 pi r that goes around, it becomes this distance, yes, and of course the height is still there. Okay, so now that it's a rectangle, and just like this, it has a depth of delta y or delta x. Now I can form the sum. Okay, so help me. Volume equals, okay? Again, just for the sake of illustration, suppose we were taking the same volume, right? So instead of delta y, I'm going to have delta x for this one. So you take the limit. Okay, I want all of the shells to be very, very, very thin. I'm going to add up again from A to B. but notice that these are x boundaries, not y boundaries. And then what's going to happen after the sigma notation? What do I put in there? Here, it came from the area of this times its depth. So this is going to come from the area of this times its depth, right? Which you saw before was 2 pi r, bless you, h. There's the area times its depth. Cool. Okay, and in exactly the same way, I can go from the sum to the equivalent integral. Okay, we took the 2 pi out because it's a constant. I said I'm integrating from a to b. And r and h, you remember, just like this big R and little r, they are functions, okay? And we want them, in this case, to be in terms of x, and then we integrate. Off we go, okay? Now, these are great methods. They're really fantastic. You've seen we've been able to approach a whole bunch of different and weird volumes with these, but the hallmark of powerful mathematics is its ability to transition smoothly between different kinds of problems, okay? Now, these kinds of problems that we're looking at, they're different. We've been opened up to a whole bunch of different volumes, but there are only certain kinds of volumes that you can do by these methods, right? Every time you get a question like this, they'll give you a function. They say, you know, here's a function or something like that, okay? They will give you some boundaries, something like this, okay? And then what other information must they provide to you for you to be able to work out the volume? You need to have an axis of rotation, right? And they'll say, you know, for instance, the x-axis or the y-axis or something like that, okay? My point is, though, that there must be some rotation. You can only work out solids of revolution by these methods, okay? Because they're round shapes, right? If you don't have something round, you can't use either of these, okay? But we can take these same approaches, right? And these are very specific to solids of revolution. And we can generalize to work out things that haven't been found by rotation, okay? Stay with me. If you haven't written this down, you should, because I'm going to refer to a couple of things on this, right? Can you tell me what's in common between these approaches? What's in common? You think about what's different, and that'll help you see what's in common, okay? What do you need to know? I think that there are 3 ingredients that go into both of these, which are generalized, okay? For instance, you've got this component. Okay, can you see that component? It's going to be the same whether you're doing it by slices or by shells. What does it signify? That delta y, what is it about? It's about thickness, or thinness, I suppose, as Apple has made. People used to say, my phone is 1 centimeter thick, but now Apple has forced everyone to say it's 5 millimeters thin. Apple, anyway. Now, it's the same idea. How are you going to cut this thing up? And obviously I can cut it up a different way if I like, okay? And in fact, you know, these are y's and x's, but do you remember I showed you this one? I think we took the hyperbola, right? And then I rotated it around this, right? And then I think we called this axis like the h-axis or something like that, okay? And then in the place of these, we had delta h's, right? So in other words, number 1, you need to know, how do we cut this thing up? Okay? In what way am I going to break this into pieces? Okay? Number 2, when I break it into pieces, what's the size, volume of each of the pieces going to be? Okay? Where is that? On each of these lines, where is it? I need a new color. Surely, it's the function, isn't it? It's the function. In this case, it's this. There's my annular disk, okay? And here, this is my unfurled cylindrical shell, okay? So number 2, what I need to know is, how big are the pieces? Okay, and they have to be related in some way, these pieces, okay? I mean, in this case, they're all annular slices. In this case, they're all cylindrical shells. But they follow the same rules. That's the important part, okay? What's the last piece that goes into this? The third and last piece. It's going to be your boundaries, right? How would you articulate that? I guess you would say, you know, how do we cut? How big are the pieces? And then, you know, how far is this shape going? Okay? What things bound it? right? So that you can know, well, I'm going to go this far, I'm going to go this far, or whatever, okay? So if I can find any kind of volume for which I can work out, how do we cut? Is there such a way that I can cut it that I'm going to get something where they're all unified by some sort of characteristics? Those pieces that share those characteristics, how big are they? And then how far do I have to go? Okay, if you can get something which matches all of those, you'll be right. You can work out a volume, okay?